Today I want to talk about a 2,000-year-old mystery story. The mystery story has to do with, first of all, a brilliant accomplishment, and second of all, a mind-boggling discovery. The accomplishment was due to a man called Euclid, who lived in a very exciting place, Alexandria, about 300 years before Christ. This was the intellectual center of the ancient universe, and Euclid was one of the most monumental thinkers of all time. He inherited from Babylon, from Egypt, and from Greece a fantastic amount of information about geometry. And he set himself the following job. He decided that he wanted to organize all of this information, starting with just a few simple assumptions and proving every single result as a consequence of 5 basic assumptions. Now, I'll show you what those 5 assumptions are. I have a drawing here. The assumptions are very simple. The first one, these are called Euclid's postulates. The first one says that between any 2 points you can draw one and only one straight line. A very simple type of assumption. The second assumption is that all right angles are equal. Now, a right angle is an angle by which you can fold a line over on top of itself. This is called a right angle. It bisects a straight angle, cuts it in half. If you draw another right angle over here, then what Euclid said is that this right angle is the same as that right angle. The third assumption was another very simple one. It says that any straight line, such as the bottom of this triangle, can be extended indefinitely. You can extend this line as far as you like. That's the third assumption. The fourth assumption is that you can draw a circle with any center and with any radius. Now, these assumptions are amazing in their simplicity. You wouldn't think that you could prove anything with them. And yet, incidentally, I've only got 4 here. I'm going to talk about the 5th in a moment because it is an extremely controversial one. With using only these 4 assumptions, Euclid was able to prove all of the theorems about what is called congruence. Now, congruence has to do with the idea that if you take, for example, a triangle or any other figure and put it down on the sheet. Now, here I have 2 triangles, each with sides A, B, and C. A, B, and C. Now, if the 2 triangles are congruent, it should be possible to put one directly on top of the other with no overlap. Let's try it. I'm going to move this triangle over, and I'll try and fit it. No, it doesn't fit. Try it this way. No. Try it this way. No. But if I flip it over, aha, it fits. This is congruent. These 2 triangles are said to be congruent. That means they're equal in every respect. All the angles are equal, and they can be made to fit directly on top of one another. The 3 motions which are allowed to be used for this purpose are sliding, turning, and flipping. These are the so-called Euclidean motions. But what was the 5th assumption? Well, the 5th assumption is the so-called parallel postulate, and it's very puzzling. It says that if you have 2 lines, such as these 2, and a third line cutting them, and if these 2 angles on the same side of the transversal add up to less than 180 degrees, then these 2 lines must meet to make a triangle. Now, this postulate is by no means as simple as the other postulates. It's by no means obvious. If you went home and talked to your little child, the little child may agree with the first 4 assumptions, but I think you'd have a hard time convincing the child of this assumption. And for 2,000 years, mathematicians were unhappy with this assumption, and they tried to replace it with a simpler assumption. They said there must be an easier way, instead of having this rather unobvious type of assumption to make. Let me tell you why Euclid came up with this assumption. He was interested in parallel lines, and he was able to prove to his own satisfaction that if you took 2 perpendiculars to the same line, these 2 perpendiculars would have to be parallel. Now, what does that mean? It means that no matter how far you extend them, they will never ever meet. How could he possibly prove that? The way he proved it was the following. He said, suppose you take these two perpendiculars and flip them over onto the other side so that they go out this way. Then, if they meet on the right-hand side, they must also meet on the left-hand side, because the two pictures are mirror images. But if they meet on the right-hand side and on the left-hand side, then you have lines intersecting in two different points. That's an impossibility. Therefore, he concluded that these two lines must be parallel. The trouble is that he was unable to prove the opposite of this. In other words, he was unable to prove that if the lines were parallel, then there must be a common perpendicular between them. He couldn't prove it. So he went back and he assumed it. And that's where the parallel postulate came from. He was convinced that it was correct based on measurements, but there was no way that he could think of to prove it, so he included it as one of the assumptions. Now, this is a very important result. I'll show you some of the consequences of the parallel postulate. One of the consequences of the parallel postulate is that the angles in a triangle add up to 180 degrees. That's a very well-known result. How does it come about? Well, this is how it does. Through the top vertex of the triangle, you draw a parallel line, and then you use the fact that since angle 3 plus this angle, y, must add up to 180 degrees, because this is a straight line here, and since this angle y and this angle up here add up to 180 degrees, therefore, this must be equal to angle 3. Similarly, here I have x plus 2 is 180 degrees, and x plus this up here is 180 degrees. Therefore, this must be equal to 2. And these three angles add up to 180 degrees, but those are the three angles in the triangle, 1, 2, 3. So that's one of the consequences of Euclid's fifth postulate. It wasn't until the 19th century that after 2,000 years of effort, that three mathematicians working in different parts of the world almost simultaneously discovered that the parallel postulate is not necessarily true. There was Gauss in Germany, Lobachevsky in Russia, and Bolyai in Hungary. And they all reconsidered parallelism, and they decided that this Euclidean assumption is not necessarily correct. Now here is how they went about it. I have here a drawing of a line at the bottom and a line up at the top. Now through this point here, you can draw lines as follows. Here's a line, it meets the bottom. Here's a line, it meets the bottom. Here's another one, it meets the bottom. And as I keep lifting the angle at the top, the line gets further and further out before it intersects. Now, sooner or later, you must come to a point, and I've indicated this by this top line here. There must be a line which will separate all the other lines into two categories. All the lines below this one will intersect the bottom. All the lines above it will not intersect. This line that separates the two families is called a parallel. And according to these three mathematicians, there's no reason necessarily why this line has to satisfy the Euclidean hypothesis that the angles down at the bottom and up at the top must add up to 180 degrees. Well, I would like to show you a little bit of this exciting adventure in thinking which led to the discovery that the assumption is not necessarily true. So bear with me. Before going into that, however, I might make a little ironic comment. 230 years before Christ, the size of the Earth was accurately calculated using the parallel postulate by a Greek mathematician called Eratosthenes. And what he did was the following. He knew that on a certain day, at a certain time, the sun shone directly down to the bottom of a well. So he got an idea. He thought, that means the sun is directly overhead. If I go 500 miles away to a different city and measure a shadow at that time. Now here I've got a drawing. This is a kind of a pillar standing up. I've exaggerated it greatly. And it's casting a shadow. because the sun's rays are parallel, the radius of the Earth has to be parallel to the sun's rays. And therefore, these two triangles are going to fit together with these parallel lines, giving me one angle here equal to one angle here. And that means that these triangles are going to be similar in shape. Not the same size, but similar. And from that, and by making measurements, you can calculate the distance around the entire Earth. It turns out that the angle is 7.5 degrees. And if you take the total circumference of the Earth over 500, which is the distance between the cities, that must be in the same ratio as 360 degrees is to 7.5 degrees. It works out to 24,000 miles, which is a very good approximation. But let's get on with the story of what happened in trying to unravel the mystery of what's wrong with Euclid's assumption. It goes back to another ancient Greek discovery, which was that the square root of 2 is an irrational number. Now you may remember the other day I mentioned that pi is an irrational number. That means it cannot be written as a fraction. What is the square root of 2? If I take a square and double the sides, I get a square 4 times as big. This raises an interesting question. How do you get a square exactly twice as big? Well, the way you do it is by cutting each one of these 4 squares in half. And now that tilted square is exactly twice as big as the original square. What is the length of this side? Well, this is 1, and this is 1. And if I use the Pythagorean theorem, it says that x multiplied by itself has to equal 1 squared plus 1 squared. Therefore, this must be the square root of 2. To the Greeks, this little construction showed that the square root of 2 is a very real number, just as real as pi, just as real as any number you might care to mention. A remarkable episode in thinking in the Greek days was the proof that the square root of 2 is not a rational number. It cannot be written as a fraction. I'm just going to briefly show you how the proof goes. If you'll focus on this argument for a moment, it's called a proof by contradiction. And this is the way it goes. It says, let's assume that the square root of 2 can be written as a fraction, x over y, not both of them being even. I square both sides, cross multiply, I get x squared is 2y squared. And this tells me that x squared must be even, because it's twice something. But a little thought will tell you that if x squared is even, then x must be even. Why is that? Well, because an odd number squared is always odd. Therefore, x must be even. If x is even, then x is twice something. If I square it, I get 4 times something. If I substitute back into this equation, I then get an equation 2y squared equals 4w squared. I realize I'm going through this quickly, but it's important just to realize that it's all very simple. Each little step is simple. When you put them together, it leads to an astonishing conclusion. Dividing both sides by 2, I get y squared is twice w squared. This means y squared is even, and that means y is even. But wait a minute. We started off the whole argument by saying not both x and y are even. If you look back up at the top here, they're not both even. Why? Why not both even? Because if they were both even, I could have canceled out a 2. Therefore, I may as well assume that the fraction doesn't have a factor of 2 in the top and the bottom. But now I've proven that no matter what fraction you write down, the top and the bottom have both got to be even. That is what's called a contradiction. There must be something wrong with this argument. There's got to be something wrong with the argument. But there's nothing wrong with any step. So what's wrong is the assumption. The assumption is wrong. The square root of 2 is not a fraction. And that's how the Greeks proved that the square root of 2 is not a rational number. What has this got to do with Euclid's parallel postulate? Well, for a long time, people assumed, of course, that Euclid, who is considered as the mastermind of the universe in terms of mathematics, everybody worshipped Euclid, that he was right, and that the parallel postulate was, of course, correct. Back about 1600, there was an Italian Jesuit priest named Zachary, and he got an idea. And his idea was, I'm going to prove Euclid was right by using a proof by contradiction, just like you prove that root 2 is irrational. And this is what I'm going to do. I'm going to take Euclid's first 4 assumptions, and I'm going to deny the 5th assumption. I'm going to pretend it's wrong. Then I'm going to reach a contradiction. And that's going to show that the 5th postulate is correct and is necessary. This man proceeded in the following fashion. This man, in fact, discovered non-Euclidean geometry and never knew it. Here's what he did. He started with a little figure. He took a base, took 2 right angles, and extended it up an equal distance on both sides, and then joined it across the top. Now, he was not able to prove that this is a right angle. You can't prove that. But what you can prove is that this angle here is equal to this angle here. Now, there's 3 possibilities. The angle at the top he called the summit angle. Those summit angles are either less than 90 degrees, equal to 90 degrees, or greater than 90 degrees. If it's equal to 90 degrees, then you can show that this leads to Euclid's geometry. In other words, if this top angle is 90 degrees, then Euclid's geometry works. Therefore, he decided to concentrate on the other 2 possibilities. Either the angle is less than 90 degrees or greater than 90 degrees. And let me show you what happened. The first thing he considered was a triangle. And he asked the question, what is the sum of the 3 angles in the triangle? Angle 1, angle 2, and angle 3. Well, here's how he proceeded. He took the midpoint of this side, right there, took the midpoint of this side, and joined them. Then he dropped a perpendicular here, here, and right down the middle here. Now, I've got this done in color, so I may as well take a look at it in color. Stands out a bit better. What you have on the bottom is one of those figures that Zachary was talking about. It's called an isosceles birectangle. The summit angles, here and here, must either be less than 90 degrees or greater than 90 degrees, or equal to 90 degrees, depending on the 3 original assumptions. By using congruent triangles, he was able to show this triangle is congruent to this one is congruent to this one, and therefore, this angle here is reproduced down here, and this angle up at the top is reproduced down here. By means of this type of an argument, Zachary was able to show that the angles in a triangle would be less than 180 degrees, or equal to 180 degrees, or greater than 180 degrees, depending on his original assumption about the summit angle. This leads to 3 different geometries. The middle one is what we call Euclid's geometry. The other 2 are now known as non-Euclidean geometries. The first one is called hyperbolic geometry, and the second one is called elliptic geometry. Now, what happens? When you try and calculate the angle at which a line first becomes parallel, you can proceed in the following fashion. First, you take a line on the base and a little altitude up here, and you lay off an equal distance. Then you take the hypotenuse, that's this distance here, and lay off that distance down here. Reproduce it. Now you take that hypotenuse and reproduce it down here. What happens? This line, the hypotenuse, continually gets a sharper and sharper angle until finally, as you go towards infinity, this line is eventually going to become parallel. The angle of parallelism is found by adding up all these little angles here. Angle 1 plus angle 2 plus angle 3 plus angle 4 and so on. Well, you might wonder, how can you add up an infinite number of angles? It's possible to do it. It turns out that a little calculation shows that the angle of parallelism in the Euclid case is 45 degrees multiplied by 1 plus a half plus a quarter plus an eighth and so on forever. Now you ask yourself, forever? How can you add an infinite number of numbers? Well, when the numbers keep getting smaller, you can sometimes do it. I've drawn a little picture here which shows what happens if I add, this is a square. Here I have on the bottom half the square, then a quarter, then an eighth, then a 16th, then a 32nd, and it does all add up. And in fact, it adds up 1/2 plus 1/4 plus 1/8 plus 1/16 adds up to one complete square. It turns out that the angle of parallelism could be equal to 90 degrees in Euclid's case, but it could also be less than 90 degrees or more than 90 degrees. Now, more than 90 degrees sounds like a contradiction. Didn't I say earlier, and I've got a picture here illustrating it, didn't I say earlier that two common perpendiculars couldn't possibly intersect? Because if they did, they would intersect on both ends. And moreover, by using a little arguing, you could show that every line would have to be of finite length and they would all have to be the same length. That sounds crazy. How could that possibly be? Well, in fact, it is possible. And if I could just show you on a ball, here I have a ball. On the ball, the shortest distance between 2 points is not a straight line, but a part of a circle called a great circle. If I take common perpendiculars from the equator, they all meet at one point up here, which is called the North Pole. And sure enough, it turns out that one of the types of non-Euclidean geometry is equal to the geometry on a sphere, which is the surface of the Earth that we live on. It's an ironic fact, of course, that geometry literally means Earth measurement. And you might say in this case that it's more sensible to say that two perpendiculars will meet than to say that they won't meet. So all of a sudden, people realized that Euclid's geometry is not the only geometry. In the 19th century, this led to a tremendous explosion, an exciting explosion developing new ways of thinking about geometry. And of course, it began to be realized that there were curved spaces. You could talk about the geometry of a curved space in which the shortest distance between 2 points is not a straight line, but a path called a geodesic. Now over here I have some examples of curved surfaces. This is a cylinder, and I've just drawn on it a sort of a barbershop type of, it's called a helix. If I were to cut this down with a pair of scissors and flatten it out into a rectangle, you would see that these become straight lines. And they do represent the shortest distance between 2 points. There's an old problem about a spider on one side of the cylinder and a fly on the other side. What's the shortest distance between the spider and the fly? Well, if you cut it down and flatten it out, you see that it's just a triangle. And you can calculate the shortest distance quite easily. I have here some other shapes. This is a cone, and it has its own geometry. This is a surface which is said to have positive curvature. A surface with positive curvature has all the curves bending the same way at any point. All the curves bend the same way. This, on the other hand, is a surface of negative curvature. In this case, some of the curves bend one way, and some of the curves bend the opposite way. That's typical of a space of negative curvature. Every one of these objects has its own peculiar geometry. It has its own laws. The angles in a triangle do not necessarily add up to 180 degrees. In some cases, it's greater than 180 degrees. In some cases, it's less. If I go back to the example of the sphere, you can easily construct a triangle which has 90 degrees here, 90 degrees here, and 90 degrees up here at the North Pole. That's 270 degrees in a triangle. In non-Euclidean geometry, or in curvilinear geometry, that's perfectly sensible. In fact, it turns out that on the sphere, all triangles, if they're similar, if they have the same shape, they've got to be the same size. You cannot make a triangle bigger without distorting its shape. And one of the theorems of non-Euclidean geometry is that similar triangles are congruent triangles. Now, this type of non-Euclidean geometry is easy to understand. The one that's harder to understand, in this type of geometry there are no parallels. The kind of geometry which is harder to understand is the geometry where there are infinitely many parallels. if you take a line and a point, there are infinitely many parallels through that point to the line that you started with. That type of geometry is harder to visualize, but it has been shown mathematically that it corresponds to the geometry of a surface of constant negative curvature. Now, I don't have an example of that surface with me, but I could. It's physically possible to draw the surface and to actually draw triangles on it, and you see in that case that all of the assumptions of this type of geometry are met. Now, you can imagine the excitement this caused in the 19th century when, for the first time, the question was asked, is our universe a Euclidean universe? Does it really satisfy the laws that we were taught 2,000 years ago by Euclid that it satisfied in terms of parallel lines? The fact of the matter is we cannot check, because if we take lines and extend them out past distant stars, how can we tell if they're ever going to meet? It took the 20th century and a man named Albert Einstein to point out that our universe, our physical universe, in fact, is probably a curved universe, and probably the angles in the triangle do not add up to 180 degrees in our universe. I have here a little illustration which shows the way in which the sun bends space around it. The very presence of the sun causes a curvature in space and causes light to travel along not straight lines, but geodesics, the shortest distance between two paths on a curved surface, except it's not a surface, it's three-dimensional space. Now, in the next program, I will be talking about a different development, and the next program after that, I will be talking more about higher dimensions. See you then.